Like you said, my name is Sean Headrick. Just a brief introduction. I started AeroTestra about 4 years ago manufacturing UAV designs. Early on I saw really these applications, remote sensing is really interesting, and so building a system that could do that was where I spent a lot of my time. So my presentation is sort of a high-level view of where I see this space evolving. We're talking about precision monitoring, remote sensing, data visualization, all of this. I think it all plays into one larger structure or ecosystem. So at AeroTestra, we are wanting to rediscover the world, but precisely. So it's applying the rigors of scientific measurement and data analysis to UAVs where it doesn't really exist right now. It's proving a use case, but not proving it to the level of accuracy that we need for science. When we look at environmental sensors, a lot of what we do right now at AeroTestra is aerial mapping, agricultural research, that type of thing. So we've touched on this already, but I'll just kind of go through a few things. What we primarily focus on is 3D topographic mapping. So we'll use images collected from a high-resolution camera. Over time, geolocated, it will create a 3D topographic map from multiple images, essentially triangulating a single pixel among several pictures to create an X and a Y and a Z, and then from millions of those points can create a topography, just like what you'd see in Google Earth, but to much, much, much higher resolution. NIR, or near infrared, not thermal, but it's the reflectance from healthy vegetation. When plants are photosynthesizing, they absorb the R, G, and the B, the red, green, and the blue, and then they reflect the near infrared. And we can look at that, the reflectance of the near infrared relative to this absorption of the visible channels to look at the health of that plant. Hyperspectral, as Christine noted also, is just a much more precise way to look at that reflectance. We work with one sensor manufacturer that says that they can see molecules, and so that's essentially what you can see, is you can define a molecule based on its spectral reflectance. And in very narrow bands, so you can define exactly what it is you're looking for. And then we get into different types of IR, long wave and short wave thermal, that allow all sorts of things, man detection, search and rescue. We can map an area of about 25 to 50 acres in about 15 minutes, and we can detect a human signature from 350 meters in the air or 1,000 feet. So if a person were lost, you can imagine how quickly we could find that person. Looking at grapes over the summer, we were able to look at the uniformity of moisture in the grape leaves based on the thermal uniformity of the whole field. So it kind of gives you an idea of what types of things you can sense. You can sense everything and start to create classifications. So whether we're talking about gas or light or anything that you'd be sensing, and then you can start to create more specific analysis for what you're looking for, what you're wanting to determine precisely. One thing that we focus on at AeroTestra, because that is what we build, is airworthy vehicles, but airworthiness generally. And so what does that mean? That means that it's safe to fly. I'm sure if any of you have worked with drones, you understand that that's kind of a precarious part of it. What I show here is a vehicle that we've built for water monitoring. It's built to land on the surface of the water, take measurements, really do underwater imaging, those types of things. But the point is it's designed as an amphibious aircraft. It's designed from that perspective, not trying to waterproof something that you buy at Fry's, because that will not work very long. It's great for proving a use case, but for long-term use and precise data acquisition, a reliable vehicle is what's going to be required. So what does safe to fly mean? It means the vehicle. So we've put many years in developing the entire aircraft. The powertrain probably costs 3 times more than some of these professional cinema multi-rotors out there. We've defined the process for building it the exact same every time. It really comes down to 99.9% of problems are going to be either in the vehicle, in the operator, or in the operation. So all 3 of these things are incredibly important, both to the safety of the operation and to the precision of how you're carrying out your experiments or your tests. This virtual environment, in the first panel, I heard a lot of the ideas on how we can visualize data, and I might be missing some here, but I think it's an interesting way to think about it. What we do right now is to create 3D topographic models. So this is kind of a representation of that, and this is what I would see as that framework, the data visualization tool. So this is what we would start with an RGB model, or straight out of Google Earth or Esri or any of these tools that are being able to use or being used to visualize this type of data. From there, we can start to either plan or just put in what we already know exists. Built up areas, residential areas, areas like wind farms or solar farms. Once we start to collect other data, and this isn't a great representation, I was struggling a little bit with how to stack these layers and explain it, but once we get different types of data and we can geolocate it, which all of the data that we would produce in our quads or in our multi-rotor systems, we can geolocate. We geolocate all the photos for a properly geo-rectified image or model in the end. But in these respects, we can georeference any type of data. We can georeference the data from people's Fitbits and stack it right in here so that we can see how perhaps pollution or heat or any of these things could affect a group of people with that sensor. The idea here is that we can just start to stack on different types of data and look at how it exists relative to the other data points collected nearby, or how they work together, how environmental toxins and heat could exacerbate that problem, and then any other types of data. So we start to get a complex, really rich amount of data just stacked in a geo-referenced way, and that seems like it's still very, depending on how you visualize it, this seems to me kind of a good way to start. And then you take this, and so now we're looking at it top down. We're able to see the layers and how they affect and how they cumulatively have different results. And then we start to apply constants to that, like time. So we know, given the time of day, what those conditions are, if they are, if it's bad air or water quality measurements or air quality measurements. And then position. So that's primarily going to deal with the position of the sun and the position of the earth. When we're looking at things like agriculture analysis, the problem right now is that what we're looking for in the reflectance of plants is a very, very narrow difference between healthy and unhealthy. So that's why we're trying to look at the absorption of the visual spectrum and the reflectance of the near infrared, and we grab that small area and we try to stretch it out in an NDVI or an exaggerated view of that. But what happens with such a small area to work with is that factors like the sun, the clouds, the direction of where that is has a great deal of impact on the final result. So we need to be able to account for that. And so that's here, we'll account for ambient light conditions with light sensors, background noise, if we're looking for air quality or water quality, we know certain measurements exist, so we can deal with that. And we start to establish standards on how we actually test. And then over time, we can start to use AI, algorithms to allow us to predict what's going to happen so that we're not really reactive as much as we become proactive. And instead of trying to save the environment, we're nurturing it. We're actively sensing its health and making changes in real time to deal with that. And so I liked what you said earlier. Every bit of data in the world is measurable. It's exciting to measure. I'm always looking for collaborators in this area, so I was very excited to be invited here today. And so if anyone would like to contact me about any projects or would like to find out more information about our company, you feel free to call me or contact me.